Okay. So we can start a new topic, duct sizing. Sizing of duct. Okay. Duct sizing means simply nothing. The dimensions of duct we have to find. A lot of things we have to discuss. Please, it will take some time definitely. Duct sizing, very important session. Duct sizing. By shape, we are having three common shape. To transfer liquid, fluid, no water, we are using pipe. To transfer air, we are using duct only. Since the density of air is 2 lesser than water, for the same flow rate, water might be required very small diameter medium, means pipe. For the same flow rate, duct might be required, air might be required large spaces. No? So, the shape of duct we are having normally, a round duct, rectangular duct, oval duct. If it is round duct, the diameter we should find. There is a duct called a spiral duct. Spiral duct is actually a round duct only. When we are constructing the surface, you can see this spiral shape. Machine manufacturing normally, spiral shape only the joints will come. So that's why we used to call that as spiral duct. Spiral duct is round in shape. Now the most common shape that we are using in the industry, that is a rectangular duct. A rectangular duct means you have to find your duct width and duct height. Always when you are noticing the duct dimension, for example, supplier duct 600 into 300, always the first dimension will be representing the width, second dimension will be representing the height only. Okay. And for good looking duct, we are having oval duct. Oval duct, even round is also good only. Oval duct, you should find your major axis and minor axis. To this axis you have to find. Actually, the rectangular duct width and height, the same only we'll be getting here as well. Slight variations can come. Okay, oval duct. Fine. Anyhow, performance-wise, the best shape is round only. When at the time of construction, we need minimum material, because the surface area, when you are comparing to rectangular and oval, minimum surface area only we will be getting. It is not too minimum. Comparing to rectangular and oval, it will be less surface area we are having for round duct. So minimum material we need in the round duct, so economical only. But still, it doesn't mean that the labor cost is less. Labor cost is almost same only will come. And also flexibility is too less in round. For example, I'm having a false ceiling. Normally duct we will be taking between the bottom of slab and false ceiling level only. See, I'm having a beam like this above the false ceiling. And here I'm having a height of 300 mm. But I'm having a duct that is coming through this way. And it is having a diameter of 500 mm. What I can do? Because I have to take my duct the other side. Either I have to demolish this beam. It is not practically possible, right? Or I have to take my duct like this. But here the diameter I am having 300, but my duct diameter is 500. You can do one thing, from 500 to 300, the duct dimension we can decrease. But the problem is, for the same flow rate, if the duct dimension you are increasing means your air velocity will, because area is reducing means your air velocity will be increasing, your pressure drop will increase there. It will create noise. At the same time, the fan has to overcome more pressure to deliver the air. So the fan pressure, static pressure will increase in that scenario. Correct, because diameter is uniform in all the directions. But instead of this round duct, if you are having a rectangle duct, for example, it is having a dimension of 500, 500. For the same flow rate, I can do one thing. Since it is 300, the height we can decrease into 250. Width accordingly we can increase. Instead of 500, the width will be increasing into 700. Say, example I am saying. Means the same, almost same cross-sectional area we can maintain. Then duct shape we can increase. Then that duct we can take to this way. So not that much velocity issue, not that much head loss issue will arise. Because a rectangular duct is flexible only. So with respect to the site condition, easily we can modify it. And so space saving will be there. Space is also a concern, because when you are placing your round or oval duct, when you are placing in the corner and all, lot of space issues can come. It's not 100%, but when you are placing like a rectangular duct, corners and all, it will be effectively utilizing the space savings. Flexible duct is rectangle. That's why normally everywhere we are using a rectangular in shape. Doesn't mean that round and oval we are not using. Definitely round and oval is having an aesthetics. That's why as per the client requirement, we can go for a round or oval duct. It's a good looking duct. Exposed duct. The duct is, there is no false ceiling. The duct is exposing, we can go for round or oval only. Okay. So before going to the duct sizing, see, 2-3 methods we are having for duct sizing. Okay. First one, the conventional theoretical method. First, I will explain theoretical method. And after that, we are having equal friction method. Equal friction method. That's the most common type of duct sizing method that we are using in the industry. Supply duct, return duct, both we can use. Whatever the duct systems it may, we can use. The next one, velocity reduction method. Velocity reduction is not applicable for big commercial purposes and all, because comparing to the equal friction, sometimes the duct dimensions will be more, and also balancing will be very difficult in velocity reduction. But the sound that is created by the air when it is flowing within the duct system is too less in velocity reduction. Sound recording studio, movie theater, wherever sound is a concern and that airflow demand will be too less, there we can go for this velocity reduction method, but not widely using. And the third method is static regain method. Even static regain, you should have a thorough knowledge in static pressure, velocity pressure, then we can do. I will explain static regain method as well. But static regain comparing to equal friction, nearly 13% to 15% more duct material we need there. So the construction cost will increase in static regain method. Also, static regain is only applicable in the supply branches. It is not applicable for return. So comparing to all this, out of these three, equal friction is the perfect method. I will explain what is it. Okay. First, I will go for theoretical method. Then I will be explaining. We can go to the real. Okay. See, duct is having certain velocity limitation. Because the maximum permissible duct velocity within the duct branch is having certain limitation. That limitation from where we can find? We can find from ASHRAE standard, or we can find from carrier standard, or if you are going to any air terminal manufacturers, means the manufacturers of grills and diffusers, in their technical data sheet, normally they used to provide the maximum permissible delivery velocity of diffuser as well as duct. There also we can find. A lot of sources we are having to find the recommended velocity through the duct. Anyhow, we can discuss two standard, one ASHRAE standard, the next one carrier standard. Carrier standard is this one, this carrier standard. For example, recommended maximum duct velocities for low velocity system heat pump. Comfort air conditioning we are using low only. High velocity we are using for industrial applications. Residences, apartments, hotel, bedroom, hospital, private offices, theater and auditorium, where you can see where this will be always good when you are selecting it. Or even if you are selecting for equal friction method, normally they are representing this noise generation, because if you are following this velocity for the main duct, starting duct, it won't create that much noise issue. So this is noise issue. But even if we are, you can select this as well. But comparing to the noise generation, this will be slightly higher only. Okay. And see, I'll be selecting this noise generation. Let's say I'm designing a meeting room. I'm designing a meeting room or a conference room. Here the velocity is in feet per minute only. And what consideration I can select? See, private offices, director room, library. Okay. This one you can select. The environment I need within meeting room, director room, conference room, the same. Maximum permissible duct velocity, I can go up to 1200 feet per minute. Meter per second into 3.28, you can convert that into feet per second. Feet per second into 60, you can convert that into feet per minute. Okay. Simply, meter per second multiplied by 196.8, you can convert that into feet per minute. Or another way, feet per minute divided by 196.8, you can convert that into meter per second. So how much meter per second this will come? Since we are following SI standard. Even this also, for example, if you want to find the duct area only I'm going to find duct area in square feet. Okay, duct area in square feet. Airflow rate in CFM divided by velocity in feet per minute. Airflow rate in CFM divided by velocity in feet per minute. You can find the duct area in square feet. So this square feet value multiplied by 144, you can convert the duct area into square inches. It is simply nothing. It's an equation called the continuity equation. I will explain that. But this method is what? IPS only. We are following SI. So that's why SI, I don't want velocity in feet per minute. I need that in meter per second. So 1200 meter per second, 1200 feet per minute, how much meter per second it can come? 1200 divided by 196.8. 6 meter per second. Correct. 6 meter per second. Okay. This one, how I found? Carrier standard. Now, when you are going to ASHRAE standard to maintain the noise as a criteria, from ASHRAE 2011 fundamentals, there is a chapter called sound and vibration chapter. There they have provided that. But this one I have taken from Air Master catalog, the same table only. There is no much difference. I am designing an office conference room. As I told, I am designing an office conference room. So see, as per ASHRAE, we got how much? As per ASHRAE, for conference room library, we got 6 meter per second. Okay. Now this one, as per ASHRAE standard, as per carrier, we got 6 meter per second. Now I am checking ASHRAE. As per ASHRAE, ASHRAE and carrier, you will not get same velocity limitations. Slight variations will come. Definitely, both are different standards only. But when we are designing as per ASHRAE, first we should find the NC value. NC value is called the noise criteria value. Means with respect to the space we are designing, there we are having a maximum sound limitation. For example, when you are designing a library, the maximum sound level should be like less than 20 decibels there or 25 decibels there. Like that, each and every spaces when we are designing, we are having certain sound limitation. So since I am designing a conference room, I am assuming it's a conference room. See, where is conference room? Office building, boardroom, conference room. This one. Conference room. NC level in noise criteria level in decibels, 3 ranges: low case, medium case, high case. Low case means the sound will be very minimum. High case means just above the tolerable limit. Safe will be always medium only. Because when you are selecting the low case, your NC level will be too less. The problem is when we are designing the system, your duct flow velocity will be too less. In that scenario, that is soundproof only fine, but the duct area will be increasing. The duct area is increasing means the construction cost will increase. The same way, high case also an issue. The problem is it will create noise at the same time. Duct dimension will decrease there, economical only, but the problem is the duct area is decreasing means the frictional losses, pressure drops will increase. Accordingly, the fan has to deliver more air, more pressure there to overcome the friction. So medium will be safe. I'll be selecting medium. Conference room, what is my range? 30 decibels. 30 dB. Most of spaces, 90% of spaces without going to any table, 30 decibel you can consider as a reference and you can do it. Okay. But some factories and all, if it is going like a 45 and all, accordingly you can select that. It's a right method. And in my case, what decibels I need? 30 decibels. After that, I have to come to this table. This table I have taken from ASHRAE, Sound and Vibration 2011 handbook. Maximum recommended duct airflow velocity to achieve specified acoustic design criteria. Okay. Carrier standard I got 6 meter per second. Okay. Here how much I will get. Anyhow, where the duct has located, that matters. Where the duct is located, the main duct location. Starting duct only we are finding now. Branch duct will decrease. You can study that. Main duct location in shaft or above dry wall ceiling means the duct is going within the building shaft, concealed within the shaft, or if the duct has exposed above the roof, exposed duct, or above dry wall ceiling means you are having a false ceiling, but false ceiling is plaster of Paris. It is not perforated grid ceiling. Fully closed drywall ceiling. That's the first condition. The second, if the duct is going above, suspended acoustic ceiling. You are having a false ceiling, but just above the false ceiling, as a layer, we will be providing acoustic insulation. Why? To prevent the reverberation and reflection of sound. Normally, that one we are using in movie theaters and sound recording studios only. Ceiling also we will be along seamless wall, floor and all they will be providing. Ceiling also they will be providing acoustic insulation. But normally we will be selecting the third condition, no ceiling condition, or the duct is located just above the false ceiling, gridded false ceiling. False ceiling we are having some openings and all, normal condition. So third condition I am selecting. As you know, my NC limitation is 30 decibel. Duct located within occupied space, design a room criteria or noise criteria, 45 decibel, 35 decibel, 25 decibel. On all the three ranges, whether it is a rectangular duct, what is the maximum airflow velocity? Where that is a circular duct, what is the maximum velocity? Okay. Anyhow, my range will come between 35 and 25, right? Because my demand is 30 decibel. For 30 decibel, rectangular duct located within occupied space, the velocity will come between 7.4 and 4.8. You can take the average of these two. Means 7.4 plus 4.8 by 2. You'll be getting that as 12.2 by 2. Let's say 6.1 meter per second. You can consider that as 6 meter per second. So whether that is as per carrier standard or as per ASHRAE standard, almost same velocity we are getting for conference rooms. Correct. It doesn't mean that always as per carrier and ASHRAE you are going to get the same velocity. Slight variations can come. Okay, in real scenario, slight variations can come. Fine. Okay, now I found the velocity. Now we can apply the continuity equation. Then I can find it. For example, just a sample. See, I'm having a small machine, a fan coil unit. And this is a starting duct. A lot of branch will come, but I just found I have to just calculate the starting duct dimension. Let's say this dimension will be, the flow rate will be 1000 liter per second. 1000 liter per second is how much meter cube per second? 1 meter cube per second is 1000 liter. 1000 liter per second. 1 meter cube is 1000 liter. So how much meter cube per second that is? After the heating and the cooling load calculation only we will do that. See, we can do a problem, don't worry. But before going to that, let me explain the theoretical concept. 1000 liter per second, that is 1 meter cube per second. We are having an equation, Q is equal to area into velocity. From this equation, Q is the same only I have explained in IPS just a few minutes back. Q is airflow rate in meter cube per second. Okay. A is duct cross-sectional area in meter square. V is flow velocity or maximum recommended velocity. How much we can go? Meter per second. In our case, Q we know. Correct. Area we should find. Duct area. A is equal to Q by V only. Correct. Q is equal to area into velocity. Area is equal to flow rate divided by velocity. So flow rate is 1 meter cube per second. Velocity I can go up to 6 meter per second maximum. Maximum 6 only. Any value less than 6 is permissible. You can keep between 4.5, 5, 5.5, anything is fine. But since we are having 6 meter per second, I'll be selecting 6. So what area I will get? Cross-sectional area of duct I'll be getting 1 divided by 6. That is 0.166. 0.167 meter square. That is my cross. So duct cross-sectional area is my fan coil unit. Duct cross-sectional area I got. So what should be the dimension? Duct might be, I'm sizing rectangular duct, square, or it might be round, or it might be rectangular. Rectangular, same dimension you can consider for oval as well. Square duct, width and height, same only. Round duct, you can find area is equal to pi by 4 diameter square. diameter is equal to area into 4 divided by pi square root. You'll be getting the diameter in meter. Correct. Like that, area we are already having this one. So area into 4 divided by pi, the value you can take the square root, you'll be getting it. Rectangular duct width and height is not uniform, right? First, I'll be sizing square duct. Square duct is clear that width into height is equal to 0.167 meter square. You can take the square root of this one, correct? Width and height is same only there. So square root of 0.167, how much you will get? Take the square root of this one, 0.408 into 0.408 into 0.408 meter, or another way, that is 408 into 408 into 408 millimeter. But this one you can round into nearest multiple of 50. 50, either you can round into 400 or you can round into 450. Because multiple of 50 ducts only we are using. But the problem, if you are rounding this into 400, the velocity will increase higher than 6, because from 408, if you are decreasing the diameter, the area will decrease. The area is decreasing for the same flow rate, the velocity will increase. So it will be good when you are rounding it. But instead of 6 is my maximum. So when I am doing this calculation, instead of 6, if I am using 5.5 meter per second for my calculation or less, like that, then this 408, even if I am rounding into 400, sometimes the velocity will be maintaining less than 6 meter per second, I can save. But since already the maximum limit I have used, the better option will be you can round that into the next one. The duct dimension will be 450 into 450 mm. Here also round duct diameter almost the same you will get. Okay. Means area into 4. Area is 0.167 into 4. Okay. Divided by 3.14. You can take the square root of this one. What diameter you are getting? The diameter will be 0.461 millimeter or 461 millimeter. We can round that into next, because since already we are using 6 meter, that problem now. That's why if the velocity I am maintaining less than 6, definitely I'll be rounding into 450. Otherwise, we can go for 500 mm. Diameter will be 500. See, in this equation, we are not considering the viscosity, so it doesn't mean that this is correct one. But a rectangular duct out of these two, either width or height, any one dimension we should assume, then only it is possible. For example, I'll be assuming the height is 350 mm. Then other dimension I can find now. So width into height is equal to 0.167 meter square. So width is equal to 0.167 divided by height is 350 millimeter or 0.35 meter. Millimeter divided by 1000. So that will be 0.35. What dimension you will get? 0.167 divided by 0.35. That will be 0.477. 0.477 meter, or another way, 0.167 divided by 0.35. 0.477. So that will be like 477 millimeter, or you can round that into the nearest multiple of 50, that is 500 mm. So your duct size will be width first, height second. So width only we have calculated, height we have assumed. So duct size will be 500 into 350. Okay. So if you are not having any software or chart, theoretically, you can go for this calculation, you can find it. But the problem, here we are not considering the viscosity, having real fluid only. Every fluid is having a resistance to the flow. Fluid will be flowing by the deformation of layers only. No, fluid is flowing by layer only. So the resistance offered by the bottom layer when it is flowing, the resistance offered by the bottom layer to the top layer, that effect is called viscosity. Water is having less viscosity. Honey is having more viscosity. Correct. Viscosity is resistance to the flow only. Even air is also having viscosity, right? So in continuity equation, since we are not considering or addressing the viscosity of flow into the consideration, So the accuracy will be less only. It doesn't mean that continuity equation is wrong. Continuity equation is okay, only somewhat near value only you will get, but it is not accurate. This is not the way we are sizing it. Okay. So this is theoretical concept. Now we can move to equal friction method. Before that, prior to start your duct sizing, we need minimum three things. Minimum three. Whatever the method you are going to follow, whether that is equal friction method, velocity reduction method, or static regain method, or even theoretical method. First thing, we need air flow rate. Air flow rate in CFM, or we need air flow rate in liter per second. Okay. See, I'm just going to this drawing. It is like two small spaces. After the heating and the cooling load calculation, we got that in the front space. This is a conference room only. Conference room. Front space, we should deliver 660 liter per second. Inside this, I have to deliver 100 liter per second by the help of, here we are having supply linear Bargill 50 mm. This one we will study in the air terminal class. Plenum sizing. Plenum sizing here we will do. This is, and here you can see this is like, in this area we are using square diffuser. 4 number of square diffuser we are having. And the square diffuser next size is 300 mm. And overall 660 liter per second has to be delivered. So 660 liter per second here, 100 liter per second here, we should deliver over 660 plus 100, 760. Okay. We know the total flow rate, but branch flow rate also we should mark. Okay. And this is written only since the machine is located outside the space it is serving. If this machine is located inside here, return duct is not mandatory. But since it is located outside, a return path has to be arranged. We can discuss that. Okay. Anyhow, let me mark the airflow rate. In this area, 660 liter per second, we have to deliver by the help of 4 number of diffuser supply. 4 supply, 4 return we are having there. 1, 2, 3, 4. So what will be the flow rate of each diffuser? 660 into 660 divided by floor only. 660 divided by 4. Each diffuser we should deliver 165 liter per second. So select this one, copy. Here I should deliver 165. Okay, 165 liter per second. And see, duct sizing means we are not sizing the length of duct. Length of duct is totally depending upon the static pressure capacity of your fan. Okay. Duct sizing means dimension of duct only. Length of duct will vary with respect to the position of your AC machine and the air terminals. And this will be 165, 165, 165. And what about here? 760 will come, 165 will go there, 165 here, remaining 165 into 2. How much? 330. So 760 minus 330, 760 minus 330, remaining we are having 430. So in this branch, I am having 430 liter per second. Starting branch 760. Okay, this is 430. Now here, definitely here you can see 100 liter per second has to be delivered. That's why 430 will come. 160 will go there. 160 will come here. The remaining, we are having 100 liter per second. Correct. Now all the branches, starting branch, this is my starting branch. Okay. Normally when we are naming the duct, this one means the first branch is called main duct. Main duct or starting branch. And further it is going straight. These are called branches. This is also branch only. And the branch that is connecting finally to the air terminal, further we are not having any connection. That is called last branch or run out. RUNOUT. But here you can see this is your main duct. This is run out only. But here I am having another branch. Here I am having another air terminal. So this is your main duct. This is your branch. These two are your run out. Accordingly, you have to find. Because whether that is main duct or branch duct or run out, recommended velocity is there. You should maintain that. Okay. So that's why here we have marked branch duct, main duct, run out flow rate. Correct. So the first parameter we got what? Air flow rate. So we need the first thing, air flow rate. How after the heating and cooling load calculation. So we have studied HAP, right? After the heating and cooling load calculation, we will select the machine. The next step, we will place the air terminal, then we will select the air terminal, we will route the duct, then we will size it. Air terminal selection we'll discuss. Okay. Air flow rate, we got air flow rate in liter per second. The next one, NC value of the corresponding space. Because with respect to the NC value, we can find the delivery velocity. We found that since we are designing a conference room, that is, I'm assuming that as a conference room, and NC value I need there 30 decibel. And the third one, maximum recommended duct velocity. Maximum recommended airflow velocity in the main duct. Not branches or not run out in the starting branch. Maximum recommended velocity, because in the starting branch, if the velocity is okay, all the other branches, it will be fine. Okay. In the direction of airflow rate, the duct dimensions will be decreasing, the same time velocity also. The velocity should not increase there. Okay. Maximum recommended velocity, we found that from the table, whether that is carrier standard or ASHRAE standard, we found that that is 6 meters. So we got all the three. Okay. So airflow rate we know, NC value 30 decibel, maximum recommended delivery velocity is also 6 meter per second. Understood. Mark that in an Excel sheet. Okay. I will be marking that. Okay. So that is duct sizing. You know, like we are designing a conference room. You know, NC value 30 decibels. Maximum recommended velocity is 6 meter per second. Any value less than 6 meter per second is fine. Okay. Otherwise it's fine. Okay. Now we can move to the first method, equal friction method. Before that, normally, first method, equal friction method. The theoretical equation that we are using for duct sizing is Darcy-Weisbach only, but ASHRAE is recommending more advanced equation that is called Darcy-Collebrook equation. Normally, theoretically, no one is going to do the duct sizing, right? Okay. As per ASHRAE duct chart or duct sizer, we can use equal friction method. See, when the air is flowing through the duct system, same like chilled water pipe we have discussed. When the air is flowing through the duct system, let's say this is my region number 1. Here I am having a pressure P1. And this is my region number 2. I am having a pressure P2. So this duct is having an area, cross-sectional area. When the duct is flowing, it will be having a velocity. Definitely, now any material is 100% smooth in nature. So the duct material will be having surface roughness. Due to the surface roughness, frictional losses will be generated. Due to the frictional losses, what pressure drop will come. So it will be clear that the P2 is less than P1. In the direction of airflow rate, head loss will happen. That is head loss. So if you want to find the dimension of duct, either velocity or head loss, we should assume. Either velocity or head loss out of these two parameters. Any one you need, you have to assume that, then only you can find the dimension, whatever the method it may. In equal friction method, head loss we will be assuming, then we will be finding the duct dimension. At the same time, velocity we will be maintaining within the limit. In velocity reduction method, instead of head loss, velocity we will be assuming, then we will be finding the duct dimension. That's the difference. Okay. Then what? First we can discuss equal friction method. So as I told, head loss due to friction, we have to select. Okay. And we have to assume that accordingly we can find the duct dimension. How? See, if we are going to ASHRAE duct sizing chapter, okay, whatever, almost all the fundamental chapters, for example, you can see in the duct sizing section, you can see this chart. In this chart, you can see the 4 parameters. X-axis, we are having air quantity in liter per second, air flow rate in liter per second. Here we are having frictional loss or head loss in pascals per meter. Okay. And 1.2, 1.4, 1.6, 1.8, these lines are velocity lines only in meter per second, velocity in meter per second. 60, 50, 63, 80, 100, 125, 160, 200, 250. These are around duct diameter in millimeter. Round duct diameter in millimeter. When we are sizing the duct in real scenario, shop drawing preparation, aspect ratio we have to consider. A lot of allowances above the false ceiling has to be considered. Hanging allowance, thermal insulation, acoustic insulation, bottom of duct to the false ceiling allowance. We can discuss that. Okay. So x-axis airflow rate, y-axis friction loss. Here we are having velocity. Here we are having duct diameter. Here you can see there is a shaded area now. Shaded area. The shaded area you can see that is starting from 0.5, 0.6, nearly approximately near to 0.65 or 0.7 to 5. This range means 0.65 to 5 Pascal per meter until this range. After that, 20 meter per second. So it is clear that maximum recommended duct velocity at any point in a duct is 20 meter per second as per ASHRAE. Within this range, you have to select. Head loss, we can go up to 5 Pascal per meter. But we will not select this 20 meter per second and all will be applicable for industrial exhaust application. Very high velocity duct. We will not go for that much. Okay. That's as per ASHRAE, this shaded range is permissible. But we will not go for that. We will not be going for that. Normally, we will be selecting, most of the HVAC engineers, 0.5 Pascal per meter to 1.1 Pascal per meter. As an average, 0.8 Pascal per meter we can select for all the design. This is SI metric. SI metric. SI metric, the head loss or frictional losses directly in terms of Pascal only. In chilled water we have discussed. Okay. Between. So normally all the system, whether that is smaller system, bigger system, you can use 0.8 Pascal per meter. But if you are going to imperial standard, IP standard, that will be slightly, unit will be changed to, that will be this one. Inch of water column only. 0.06 to 0.13 inch of water column per 100 feet of duct work. Each 100 feet of duct length, this much water column of pressure drop can come. Those things already we have discussed yesterday in the pipe sizing session. Same. As an average, 0.08 inch of water column per 100 feet of duct you can discuss. Each 100 feet of duct length, 0.08 inch of water column, pressure drop we can come. P is equal to pressure is equal to density into gravity into water column. By that equation, we can convert that into Pascal as well. We can convert that. You know how to do it. Correct. This is IPS range. Okay. Correct. So this is a normal range we are selecting. Otherwise, we can find. Suppose this is a normal range as we are following. Suppose if we are using, people might be saying like a 0.06 or 0.08 or 0.13. What exactly has to be selected? Easiest method, you know the velocity, right? For example, if starting branch, here we are having 760 liter per second. Maximum velocity I can go up to what extent? 6 meter per second, right? Mark this 2 parameter in the table. The duct sizer also it is possible. I am selecting this one. Where is 6 meter per second? Okay, where is 6 meter per second? So let me select 6 meter per second line. That's a maximum. Any value less than 6 is fine. Even you can select 5.5, no problem. 6 is, this is 6 meter per second. Okay. And what's the flow rate we need? Starting branch flow rate is 760 liter per second. 760, where we will get it? This is 500, 600, 700, 800. In between 700 and 800, middle side 750. Slightly here you will be getting 760. Make a straight line that will be coinciding on this point. There you can find the duct diameter at the same time. There you can find the head loss as well. That round duct diameter you can see. If you are following for round duct diameter, the round duct diameter in this point will be 400 millimeter. The round duct will be 400 millimeter, and the head loss in that scenario is coming between 0.9 Pascal per meter to 1 Pascal per meter. Correct. Here only we are getting that. How much we can consider? 0.95 Pascal per meter. So this is your head loss for all the other branches. You can select this 0.95 Pascal per meter. Using this 0.95 Pascal per meter line as a reference, all the other duct branch we can size. Like that also we can find the head loss. I told normally we will be selecting 0.8 Pascal per meter, not required. If you know the velocity limit, first branch we have to size with respect to the table. Then with respect to the first branch, we can find the head loss 0.95. Using this 0.95 Pascal per meter, all the other branches we can size. Like that also you can do that. Understood? Now 0.95 I can make a straight line with respect wherever the flow rate is coinciding at that point. There I can find the velocity. Okay. So like that also the design engineers used to follow. Okay. But companies normally they're following this range. Okay. 0.5 Pascal per meter to 1.1 Pascal per meter. This is just a reference range only. Just it will vary when we are adjusting it. As an average, all the system you can select 0.8 Pascal per meter. Whatever the system it may, all the system you can use 0.8. For example, if you are doing the duct design by Revit MEP software, Revit MEP predefined with the 0.8 Pascal per meter for duct design. We can change that. That is another story. But the problem is for higher flow rate. For example, if you are having a fan coil unit that is located within the space, so in most of the cases, the velocity will be limited to 6 meter per second. Correct, 6 meter per second. We finding the value of head loss in case of equal friction method, we have to assume it now. No. In this method, we are not assuming it, right? In this method, what I did, here you can see, I told 6 meter per second line, that's a maximum velocity. And I plotted that. From there, I got a point. That one you can use. Okay. Like that you can follow. But why we are using this one? Which one? 0.5 to 1.1. If you are following this 0.5 Pascal per meter to 1.1 Pascal per meter, most of the cases, the velocity will be less than our NC limit. So in that scenario, you don't want to go for any NC checking and all. Velocity will be always fine there. But we have to verify that. But even though 0.8, whether that is smaller machine system or bigger machine system, smaller means like a fan coil unit, ductable split AC, bigger means like air handling unit, FAHU, heat recovery unit. Every system you can design 0.8 Pascal per meter, but the problem, you have to make sure that the starting branch velocity will be within the range. Because in certain condition, for ductable split AC, if the flow rate is high, if you are using 0.8 Pascal per meter, sometimes the velocity will be coming higher than 6 meter per second. In that scenario, what you have to do, instead of 0.8 Pascal per meter, you have to go for less. That's why most of cases when we are designing the system, mini equipments, small equipments, means equipments that is located concealed or concealed above the false ceiling. Fan coil units, ductable split ACs, okay, DX units. Capacity maximum, average capacity maximum 5 tons of refrigeration only. But Panasonic and all, it might be having 8 tons of refrigeration as well. Okay. Anyway, many equipments in this range, you can go for 0.5 Pascal per meter your design. Then your velocity will be fine there. Big equipments like bigger equipments, high capacity equipments like air handling unit, fresh air handling unit, or energy recovery, heat recovery unit, even if exhaust systems and all, you can use 0.8 Pascal. But whether that is mini equipment or bigger equipments, doesn't matter. All the system, you can use 0.8 Pascal per meter, but you have to make sure that the velocity is within the range. But if you want to safely design it, mini equipments, you can use 0.5 Pascal per meter, bigger equipments, 0.8 Pascal per meter. Like that, you can design your systems. Okay. Clear. And as you know, whether there is bigger equipments or smaller equipments, velocity ranges normally, in some cases, industrial application and all, as per ASHRAE career standard, industrial application, duct velocity, we can go up to 2,500 feet per minute. Okay, means 2,500 piece. That is fine. 2,500 divided by 196.8. How much? 12.7 meter per second. But we will not go that much. Okay, because sometimes it will create some noise. Normally, we will be maintaining. Industrial exhaust you can go, no problem. But rest all the cases, no, means comfort air conditioning system, hospital, hotel and all, try to maintain less than 9 meter or 8 or 9 meter per second. Means maximum 1,800. Bigger machines, I am saying, starting branch velocity. For example, when you are considering the noise criteria as a parameter, maximum velocity they are recommending 1,800 only. How much it will be? 1,800 divided by 196.8. It will be 9.14. So 8 to 9, 8 meter per second. So this AHU, FHU, okay, heat recovery unit, starting branch velocity, bigger machines, you can go up to 9 meter per second. Or even if it is 10 meter per second, fine, but that should be in the controlling factor. Here you can go up to 10. Okay, even. So try to maintain less than 10. Between 8 to 10 is fine. They are offering 9 meter per second between 8 to 10. But it should not be higher than 10. It will create some noise. But exhaust and all, even if it is going like a 12 meter per second, all that is fine. Car park exhaust and all, because sound is not a criteria there. There you can go for 12 meter per second. Starting branch velocity, that is fine. But if sound is a concern there, definitely the velocity you have to control accordingly. Okay. Now, I'm just going to size my duct. See this one, first one, 760 liter per second by the help of chart first, then duct sizer. See, I'll be following 0.8 Pascal per meter. As I told, all the system, or this is a mini equipment only, definitely you can go for 0.5 Pascal per meter. Bigger equipment, 0.8 Pascal per meter. But whatever it may, 0.8 Pascal per meter, you can select for all the equipment. But if the velocity is okay, it is fine. No? So let me try for 0.8. If it is 0.8, I'll be going for 0.8. Otherwise, I'll be decreasing less than 0.8. Let me select 0.8 Pascal per meter. 0.8 Pascals per meter as an average. Where it is 0.3, 0.4, 0.5, 0.6, 0.7, 0.8 Pascal per meter. Correct. This way. Okay. And what's the starting branch flow rate? 760 liter per second. Okay. And the coinciding point you will be getting here, here. And what is the velocity there? This is a velocity line parallel to the velocity. This is 5 meter per second. This is 6 meter per second. So my velocity will be just 5.5 or 5.6 meter per second. No, that is perfectly okay. Why I should go for 0.5 Pascal per meter? If this velocity was coming higher than 6, then I'll be going for 0.5, because comparing to 0.5 or 0.8, comparing to 0.8, if you are following 0.5, if the frictional losses is area, velocity, frictional loss. Velocity and the frictional loss is directly proportional only. The velocity is increasing, head loss will increase. But both these values are inversely proportional to area. If velocity is increasing, area of duct will decrease. Head loss is increasing, area of duct will decrease inversely. Correct. So that's why instead of 0.8, if you are going for 0.5, the area of duct will increase. You need more material for duct construction. So even if 0.8 Pascal per meter is as per ASHRAE ranges only, even velocity is also fine in my range, definitely go for 0.8 Pascal per meter. 0.8 Pascal per meter is 0.08 inch of water column per 100 feet of duct. CFM, accordingly you can find. Okay. So I got the diameter. How much? Diameter, see, here only I'll get the diameter. Diameter is getting between 400 and 500. If suppose it was getting somewhat in the middle, I can say that is 450. Anyhow, round duct only this one. Suppose here you are having 315 mm, 630 mm. These diameters are not available. Multiple of 50 only is available in the market. Okay. Anyhow, if I was getting this coinciding this line in the middle, I can take 450, but it is somewhat near only. So I'll be taking that as 420 mm. Clear? So starting duct diameter, I will be getting 420. It's not finished, just starting only. Let's say this, I am getting a round duct dia 420. But if you are using round duct dia, definitely you should go for not 420, you should go for 450 mm, because 420 normally we are not using, 450 only. But I need rectangle. I don't want round duct. A round duct, that is fine. 420 mm I got. Round duct, that is fine. I need rectangular duct. Rectangular duct, ASHRAE has provided on table the fundamentals just below. This. In this table, circular equivalent of rectangular duct for equal friction and capacity. Okay. See, duct is having a term called aspect ratio. I am going to explain now. Before that, here you can see we are having two dimensions because duct is having two dimensions. One dimension is A, another dimension is B. Because I should find, now we got the diameter. Now equivalent dimension of rectangle duct I should find. Top side you can see 100, 125, 150, 175. This is length of one side of rectangular duct. Whether that is width or height, whatever it may, one side. In the first cell you can see here 100, 125, 150, 175. This is other side only. And all this we are having here, this one. These are circular duct diameter we have taken from the chart or from the graph. How much we got? We got our diameter is 420 millimeter. Okay, 420. So 420, you have to check in the first cell. Where is 420? When you are checking it, 420 is not there. 417 is there. 424 is there. 417 and 424. Which one is near? 417 to 420, 3 difference. 3 mm. This is 4. So 417 is near. So when you are selecting, this is equivalent at 417. One side you will be getting 2300. Other side you will be getting 100. Means this is not possible. One side you will be getting 2300. Other side you will be getting 100. That's a duct dimension. If you are going to the next session or the third one, where is 420? 420 is not there. 426 is there. So the duct dimension, one side is 1300. Other side is here you can see. How much? 150. But this size is not possible. Why means we have to follow, when we are sizing the duct, we have to follow a term called aspect ratio. Aspect ratio is length by breadth only. But for easy understanding, in terms of duct, you can say there is bigger dimension of duct or bigger side of duct in millimeter divided by smaller side of duct. This ratio should be less than 4. Aspect ratio should be always 4:1 or 1:4. Optimum aspect ratio. Optimum aspect ratio is 1 only. Means aspect ratio between 1 to 4, any sizes are permissible. Less than 1 or higher than 4 is not permissible. But as per the site condition, if there is no other choice, then in certain condition you can violate it, because as per the site condition, if it is not possible to provide aspect ratio 1, we have to violate this one. That is another story. But as much as possible, try to maintain aspect ratio 1, because it is not 90% of cases aspect ratio 1 duct is not practically possible, because above the false ceiling, most of the time we are having very limited space only. So aspect ratio 1, sometimes it is not practically possible. That's why. What's the problem? What is the reason why, if the aspect ratio 1 is increasing, what problem we can face? See, duct surface area will increase. Comparing to aspect ratio 1 duct, aspect ratio 1 means bigger side and smaller side is same. That is called the perfect square. For example, bigger side is 200, smaller side is 200, 200 by 200, aspect ratio you will get 1. Perfect square. Aspect ratio 1 duct is having minimum surface area. So we need minimum material for duct construction. When the aspect ratio is increasing from 1 to 4, the surface area of duct will be increasing. Accordingly, the construction cost of duct material cost will increase. Definitely more material we need. Nearly 25 to 30% of more material sometimes we required with respect to the duct dimensions. That's why nearly 30% of duct material cost will increase sometimes. But 4, I am saying 1 to 4. If it is 1.1, 1.2 and all, it might be less only. That is one. Construction cost will increase. The second thing, duct we are proposing definitely thermal insulation. Correct. The full outside we are providing thermal insulation. So duct heat gain means higher temperature to lower temperature, duct will be getting heat, no? That we can prevent up to a certain extent. But no thermal insulation is 100% efficient, right? Comparing to duct 1, duct 4 is having more surface area. More surface area means more heat gain. So even if we are providing thermal insulation, comparing to aspect ratio 1 duct, aspect ratio 4 duct will be getting more heat gain inside. Okay, that's why aspect ratio 1 try to maintain always. That's why by the help of this table, if you want to find aspect ratio 1 duct, you have to check in the first diagonal. I'll explain. What is the round duct diameter we got from the table? Round duct diameter we got for 20 mm. 420 mm. Now in the first diagonal, check where is 420. 420 is not there. 437 is there. 437, 420, 437 and 492. In between it will come. The 383. So 383, 420, 437. Here the different distance is just 17. This one will be more, no? More than 33 it is coming. So which one we can select? 437, because exactly 420 you are not going to get there. Somewhat near. Which one? 437. So when you are selecting, this is our round duct diameter. Top side you will be getting one side 400. First column you are getting other side. That is also 400. So your duct dimension will be 400, 400. Aspect ratio 1. The same time, you can check this diameter 420 in the next cell. 122, 150, 117, next diagonal 204, 232, 259, 283. Where is 420? 420 is not there. 409 is there. That is nearer. So the duct size will be getting 350, 400. That is decreasing, right? 409 slightly. So it will be good if you are going for 464. 464, you will get 400, 400. Correct. So we'll be getting 400, 350. Okay. Means aspect ratio is increasing there, no? That's why from the first diagonal to downwards, if you are moving, aspect ratio will be increasing from 1. Correct? So you have to select your head loss 0.8 Pascal per meter, mark it there, find the round duct diameter, come to this table, check in the first diagonal, then you can find the aspect ratio 1 duct. But as I told, aspect ratio 1 is not practically possible always. Why? Allowances has to be provided. Duct we will be hanging above the false ceiling only. So we can discuss the allowances. These are the standard allowances only for general conditions we are using it. This is my finished floor level and this is my false ceiling level. Let's say this is my duct. Okay. Duct I should provide hanging allowance. Normally duct we will be hanging only. No? We will be hanging like this. So this is my bottom of slab and this will be top of duct surface and this will be bottom of duct. If you are having insulation, then top of insulation, bottom of insulation, like that it can come. This is without insulation. This is my top of duct. So this one, no, hanging allowance. Allowances for hanging allowance, how much you should consider? Means bottom of slab to the top of duct. See, minimum 100 mm you should consider. 100 mm, because your duct should not touch there. Sometimes it might not be practically possible. Even if that is very congested, at least 50 mm try to maintain, 2 inches. Because your small minute gap should be there. Otherwise, your duct will be touching your bottom of slab. No? Minimum, if you are getting 100 mm or any value higher than this is fine. We are too happy. So try to maintain 100 mm first. If you are not getting 100 mm, go for 50. Minimum 100, 50. I'm just for safety. I'm saying congested cases, you can go for that. Okay, because your duct should not touch the bottom of slab. The next one, bottom of duct to the false ceiling. Normally, in some, not in ASHRAE, some handbooks they are offering like a 6 inches, 150 mm. Why means our light fittings, cables and all, it is going through this way only. So that's why they are offering 6 inches is not mandatory. So that's why bottom of duct to the false ceiling, maintain at least 100 mm. 100 mm there you need, but as I know, at least 50 mm in very congested cases, you can go for that. You need gap there. Okay. The third one, thermal insulation. Thermal insulation, we will provide top side, bottom side, right side, left side. All that side we will be providing thermal insulation. But left side and right side doesn't matter because that is affecting the width of duct only. Normally, we are finding the allowances with respect to the height only. Width, if it is mandatory, then rare only. Height only, we are facing issues. Width above the false ceiling, we are having a lot of spaces. Width, we will not face much issues. We will be facing issues in height only. So that's why I am calculating the allowances in height. How much? With respect to the type of insulation material, it may vary. Nitrile rubber, it might be less than 25. Some measure. But normally, glass wool, if you are using, 25 mm thickness has to be provided for inside a duct. Outside duct, 50 mm. But that is also with respect to the conductivity of the thermal insulation material and thickness as well. Conductivity we can find from insulation chapter of ASHRAE. Conductivity. If you know the conductivity value, you can find the thickness. Resistive R value is also there. Conductivity value we can find from there. No, which one? This table. Insulation chapter. Resistance required R value also is there with respect to the climate zone. If you know this X value and R value, the thickness of insulation we can easily find. That in the insulation chapter we can study. Anyhow, normally for maximum inside duct we will be having insulation of 25. That's a maximum. For glass wool it is coming. Means 25 mm in the top side, 25 mm in the bottom side. 25, 25. So overall how much? Thermal insulation 50 mm. There is no other allowances for that. So overall, but here, let's see, I'm not considering acoustic insulation. Acoustic insulation, I will explain next step. Here the allowances how much? 100 plus 100 plus 50. 250 mm allowances has to be deducted. See, in my case, the maximum permissible ceiling height, Here you can see bottom of slab to the false ceiling 600. Standard offices and all, normally 600 only we will get. Sometimes we'll be getting higher than that. Sometimes we'll be getting less than that. So bottom of slab to the false ceiling, in our case, this is 600. Sometimes if you are having like a beam and all, then this is bottom of beam to the false ceiling. That height has to be selected, because otherwise we will not get the continuity. Bottom of beam has to be selected. But here we are not having anything like that. Bottom of slab. Okay. So now bottom of slab to the false ceiling. Available ceiling height. Available ceiling height is 600 mm. Now maximum permissible duct height. Maximum permissible duct height is 600 is the maximum. Allowances 250. In any case, the height of my duct should increase higher than this. Should not, right? 350. Okay. So keep this in mind. So allowances without acoustic insulation, I'm not considering. Okay. Maximum permissible duct height without acoustic lining. Acoustic insulation allowance is also considered. How much it is? 350 mm in my case. Okay. Now, see, when we are sizing the chart, using chart when we are sizing it, what diameter we got? Diameter we got 420. So from the table we found that is 437. Okay. The duct dimension I got 400. 400, correct. Means width is 400, height is 400. Is that possible? That is not possible, right? Because maximum permissible, now the duct height as per my site condition is 350 mm only. So my duct height should be less than that. In that scenario, top side, this one you should consider as your height. Means maximum permissible duct height is 350 only. Now, where is 350? You can say 350 until 900. Duct dimension higher than 900, you can find below. Here. Below also it will continue. Okay. So anyhow, my case it is 350 only. Maximum permissible duct height is 350. Now, in this column, I should check where is 420 mm round duct dia, circular. 350, 420 is not there. Which one is near? 409 to 420. 409 to 420, 11. 433, 12. Which one is near? 409 only. Both you can select. I am selecting 409. Duct dimension you will be getting 350. Other dimensions you will be getting 400. Frictional drop will be slightly higher in that scenario. So now we got the duct dimension. Width first, height second. Okay. This is height only. So duct 400, 350. You can mark SAD 400, 350. Okay. So instead of 760, suppose if I am having 1000 liter per second there, 1000, what I can find? 1000. Maximum permissible duct height is 350 only, 1000 liter per second. So where is 1000? Let's say this is 500, 6, 7, 8, 9. 1000 liter per second, 0.8 Pascal per meter. This is a line. Even though for that case also the velocity is on the boundary only, 6, fine. If this velocity is coming, for example, same. If the velocity, if the flow rate is like 2000 liter per second, anyhow, FCU, that it will not come that much. 2000 liter per second and all, if you are selecting 0.8 Pascal per meter, there the velocity will come 7. In that scenario, I can't use 0.8 Pascal per meter. There I have to decrease it, 0.7, 0.6 or 0.5 you can select. 0.5 is safe side. Most of the time the velocity is limited. Anyhow, I don't want this one. 1000 Pascal per meter. The velocity, how much I am getting? 6 only. No, this is 6 meter per second. Fine. Less than 6 only. What diameter I am getting there? Diameter I am getting between 400 and 500. This is middle only. middle, slightly higher than that. Okay. How much? 450, 460, 470. You can select that as 470 millimeter. Okay, 470, let's say. Now I am just going to this table, diameter 470 mm. Okay, 470. What should be the duct dimension? Aspect ratio 1 if you need. Where is 470? 470 is not there, 492 is there. Aspect ratio 1 if you need, the duct dimension will be 450, 450. Aspect ratio 1 you will get. But aspect ratio 1 is not possible in our case, because in our case, the maximum permissible duct height is 350 only. So you have to round the 350. Now from here you can check it. Okay. From here, 350, where is 470? 470 is not there, 477 is there. Correct. From here you can find 550. Now you can say your duct height is 350, width is 550. Any height less than 350 is permissible, but if you are going like a 300 and all, again the aspect ratio you will losing. Right. So 350, other dimension is 550. You will be getting the supplier duct 550 into 350. Clear? Like that we have to size it. Anyhow, in the real scenario, following this table and all, that is very rare only. So the same equal friction method we can continue in the next session using DUCT SIZER software. Not only this parameter, lot of other things, just I have explained one, not only these parameters, there is a lot of other things has to be discussed, because when we are sizing the branch duct, the neck size has to be considered. Flexible duct diameter has to be considered for the selection of the height. A lot of other things will come. So it will take some time to finish the duct sizing. 2-3 classes it will take. Okay. So in the next session, we can start duct sizing using duct sizer, and we can discuss EQ velocity reduction as well. And